Now that we've found the Fourier transform of e to the minus at ut, let's take a little bit more look at the details of this. So we have a frequency response now, and we want to now break this down so that we can understand the amplitude response, and we also want to be able to understand the angle and phase response. So remember, we could rewrite our frequency spectra as being equal to the magnitude multiplied by an exponent raised to j of the angle, where the magnitude of the frequency response we can call the amplitude response, and that theta g we can call the angle or the phase response. So in this case, or any case where we have an imaginary number, we can find the magnitude response as being equal to the square root of the real part of the imaginary number squared plus the imaginary part of the imaginary number squared. And we can also find the angle of this by taking the inverse tangent of the imaginary part divided by the real part. And for any complex number, this might be a little bit easier to see if we just remember it this way. So if we have some some imaginary number given in rectangular form, it'd be equal to z equals a plus jb. And we could find the magnitude response like this, and we could find the angle by taking this inverse tangent, and then we could rewrite this as the polar form of the imaginary number. Okay, so now that we have those definitions in mind, let's take a look at how we can find the amplitude response. So there's a little trick that we can do. Let's break up this frequency response into the numerator and the denominator, and we'll just call the numerator g sub 1 and the denominator g sub 2. So if we want to find the amplitude response, then instead of taking the whole frequency response and then trying to turn this into one imaginary number, it's going to be a little bit easier if we just find the magnitude of the numerator and the magnitude of the denominator. So we'll do that in just the same way. So we'll take the real part of the numerator squared, the imaginary part of the numerator squared, and then we'll take the square root of all of that. Then we'll divide it by the denominator while doing the same thing. If we do that, we will see that we're going to get the amplitude response is equal to the square root of 1 squared plus 0 squared divided by the square root of a squared plus 2 pi f squared. And if we simplify this, we'll get 1 over the square root of a squared plus 2 pi f squared. So that's the amplitude response, but what about the phase response? So let's take a look at the phase response. And we can do the same trick with the phase response with just one slight modification. So we'll again call the numerator g sub 1, and we'll call the denominator g sub 2. And because it's the angle, remember we would rewrite this. We would write this as e to the j theta g1 minus e to the j theta g2. So that means that the total angle of this could also be rewritten as the angle of the top part minus the angle of the bottom part, the angle of the numerator minus the angle of the denominator. So we'll do this in 2 steps. We'll find the angle of the numerator, we'll find the angle of the denominator, and then we'll subtract the denominator from the numerator. So if we rewrite it this way, in a formal mathematical way, it would look like this. But just looking at the frequency response, we can plug in these values, and we can see that the first part we have inverse tangent of 0 over 1, so the inverse tangent of 0 minus the inverse tangent of 2 pi f over a. But if we think back to what inverse tangent looks like, we can see and remember that the inverse tangent of 0 is just going to be 0. So this is all going to simplify down to an angle response of the negative inverse tangent 2 pi f over a. So if we take the work that we've done and rewrite this, so we have the amplitude response that looks like this, phase response that looks like this. We could rewrite the whole frequency response to look like the amplitude response multiplied by e raised to the minus j inverse tangent 2 pi f over a.